Okay. Uh,
Dr. Mukesh, can we start or?
yes, sir. Yes, sir. We're going to start. Good evening and a very warm welcome once again to speaker and participants joining us today. I request once again all participants to kindly keep their microphones muted and use the chat box for any technical queries. Uh, for today's second session, we are pleased to have Professor Aditya Trivedi, sir. Good evening, respected sir. A very warm welcome to the AICT sponsored Atal FDP. Thank you for joining us. It is my great privilege and honor to introduce today's distinguished speaker, Professor Aditya Trivedi, sir, an eminent expert in the field of communication system. Uh, Professor Aditya Trivedi is a distinguished professor in the Department of Information Technology at ABV-IIITM Gwalior, India. He hold a PhD from IIT Roorkee and MTech from IIT Kanpur. He is a senior member of IEEE. Professor Trivedi is having 3 decades of academic and research experience. He is currently serving a professor HEG grade at ABV-IIITM Gwalior since July 2019. He also held an international academic engagement as a visiting faculty at, at the Asian Institute of Technology, Bangkok, Thailand, uh, in January to May 2020. Professor Trivedi recent research leadership includes serving as PI of a faculty initiation grant of project of rupees 1.615 crores. The project focus on developing meaning-aware, semantic learning-driven communication framework for the next generation networks. His scholarly contributions include several patents, more than 60 journals, publications, 120 conference papers, and 5 book chapters. Thank you so much, sir, for joining us today. Now, sir, over to you. You can start.
Thanks, Dr. Mukesh. I think you gave very elaborate introduction that was not needed actually. Anyway, so let me share the screen. In just a minute. Screen window. So is the screen visible to all of you?
Yes, sir. Yes, sir.
So let me start with this future trends in quantum communication. So basically, we can see the features of 5G technology. Every day now we are talking about 5G, 6G, 4G, things like that. So what is the features of the 5G technology? Right now, this 5G technology is also being rolled out in our country as well, because that has started in 2020, and this is also being rolled out. And some places also we are still dealing with the 4G network and 3G network as well. But all these technologies are basically backward compatible. So this suppose that your handset is of 5G, then it is basically can also work on 3G as well as in 4G. My voice is clear or the volume is okay?
Yes, sir. It is clear, sir.
Mukesh, my volume is okay? This
Yes, sir. Yes, sir.
okay. So another there are some features of the 5G technologies basically compared to this 4 and 5G. This basically gives you a 10 to 100 times improvement. And the latency is basically the delay that occurs from the your handset to the base station. That is the overall delay is basically known as the latency. Latency has got multiple delay components, but the combined combination of all the sum of all the delays basically gives you the latency. So that 1 millisecond latency is basically prescribed for the 5G technology. And also the bandwidth per unit area is also 1000 times and 100 times more number of connected devices for the unit area compared to the 4G LTE. LTE stands for the long-term evolution basically. So, so the talk basically discussed the future trends in quantum communication, an area that is becoming increasingly significant as we move into the era of 6G and beyond. So quantum communication represents a paradigm shift from classical communication because it draws on the laws of quantum mechanics. That is something actually that normally the communication here doesn't do basically. So basically it involves a part of physics as well. Quantum mechanics, mainly superposition and entanglement, to enable fundamentally secure data transmission. Basically, why this we are going for this quantum communication? Because the basic thing underlies is that the protocols that we are using for the security purpose, they are susceptible and they can be very well broken with the help of quantum computers. So that's why we need new methods so that we can have secure communication in the era of quantum computers. That may take place around 5 to 10 years. It may come into the market. Just wait. Just wait. Okay. So as global communication network expand, and as the new technologies like AI, artificial intelligence, autonomous system, and massive IoT continues to evolve, the requirement for ultra secure and tamper proof communication becomes more critical. So quantum communication basically promises exactly that. It enables capabilities such as unconditional or secure key distribution, long distance entanglement, and probably tamper evident channels. So this basically particular slide connects quantum communication to the limitation of the current systems, like its relevance to the 6G networks and the transition towards quantum safe cryptographic solution. As I just mentioned, that the quantum computers can break all the standard cryptographic algorithms which are currently in use. So this foundational understanding will help appreciate why the world is moving rapidly towards quantum communication technologies. Okay. So then we can go to the next slide. So this is basically the features of 5G technology. As you can see, this figures is all has got many components, like somewhere you can have autonomous vehicles is there, smart cities also there, e-health remote monitoring system is also there, traditional base station communication is there, UAV is also there, underwater communication is there. So many parts are there. So basically the 5G encompasses a lot of technologies. Basically micro cells are there, so many things are there in this 5G technology. So basically these figures give you some idea basically what different kind of basically applications are being evolved using this 5G technologies, like robotics is also there, automation is also there, things like that. Okay. So this figure is basically meant for this. And also you can see there is a UAV network is also there. You can see this UAV network is also there. Okay. Things like that. So this I am highlighting also. Underwater communication is also there. Things like that. So basically the 6G wireless communication that is likely to take place somewhere in the basically in the, say you can say that 2030 it is proposed, or you can also roll out a little bit early also as well. So basically in the 6G wireless communication, it tries to basically cover the some drawbacks in the 5G. So what are the drawbacks could be 5G? 5G itself is you can see as compared to 4G, it has got much more capacity, but 6G is even going a step further in this direction. So compared to 5G, 6G gives you basically more capacity, and it gives you more data rate, and also quality of service is low in the case of 5G. So this we are going to improve in the 6G, things like that. And so as we can see, compared to 4G, 5G is encompasses many more technologies. So 6G even a step further into that. So now the introduction to this 6G wireless communication. So it is basically, as I told you just now, it is expected to be deployed in the year, say 2027 and 2030. So as we can see, this 6G wireless communication is basically gives you high system capacity, even lower latency, and the great improvement in the quality of service, and also full support of artificial intelligence. It is not that 5G is also not using 5G is also using some kind of artificial intelligence, but this artificial intelligence is going to be completely integrated into the 6G. So 5G is also used, but 6G it is part of AI is going to be part of the 6G communication. So it provides new services and improves all past services compared to 5G, and also it can handle the large volume of data. So, like it also involves some other technologies like terahertz communication. Terahertz is very, very high frequency communication. It can go for it. And optical wireless technology, free space optic networks, blockchain, three-dimensional networking is there. So the high data volumes could be there in the case of 6G, as well as some unconventional technologies, as I just mentioned, like terahertz communication, optical wireless. All these things are going to be integrated. And for the security purpose, as such, blockchain for the trust management and for three-dimensional networking involves drones and satellite. Satellite would be a part of that also. So this overall 6G is being designed as a highly intelligent, you can say ultra secure and globally connected communication framework. Okay. So now these are some features of the 6G technologies basically. So 6G introduced several groundbreaking features. One of the most highlighted capabilities achieving per user data rate as high as 1 terabit per second. So you can imagine that we are going up to 1 terabit per second in the 6G. So this is several orders of magnitude higher than the 5G, because 5G normally it is going to be 10 GB. So now it is 100 times more than that basically. So 1 terabits per second. So it is basically enables seamless holographic communication. You can project basically holographic. Basically, you can project as if you are talking in the virtual reality. You are just talking. Suppose that you are communicating with the person, and the person it seems to be just standing in front of you. Things like that. So ultra high, ultra HD, immersive media, advanced autonomous applications. So many features would be encapsulated in this 6G technology. So another important feature is basically low latency, less than 1 millisecond, making real-time interaction even more reliable than before. As the latency is lower, that means you are going to more and more real kind of interaction, a more realistic scenario. So 6G also aims to maximize quality of service, like ensuring consistent performance regardless of the user density of the or the environmental constraint. Because sometimes what happens is that there is a some environmental constraints are, for example, there is a some rains are going. In that case, there is going to be more absorption of the signal, so that gives you some kind of fading effects and things like that. So 6G is going to be beyond that basically. That irrespective of the environmental constraint, or even if the user density is more, in that case, what happens is that normal, traditionally, we can see if the user density is more, in that case, the overall data rate per user is basically comes down. But this is not going to be there in the 6G technology. So in addition, the 6G will leverage a variety of emerging technologies. So these include this AI-driven resource optimization, like and quantum communication for security, terahertz bands for the ultra-high speed transfer, and could be integrated terrestrial and non-terrestrial. Terrestrial basically the traditional base station kind of communication. Non-terrestrial means basically you are going through some UAV or you are going through some satellite communication, things like that. So these technologies collectively act as a driving force behind this 6G, enabling truly intelligent and high performance digital kind of this ecosystem, you can say. So with these capabilities, 6G is expected to surpass all earlier generation, because every generation basically includes some kind of enhancement in the features like speed, security, connectivity, and all these things. So 6G is going to be basically perform much better than the 5G, things like that. So now we are having this evolution of mobility security landscape from 4G towards 6G. So as you can see, the slide contains basically three things. 2010, that is 4G basically, when the 4G was launched, long-term evolution or LTE advanced. The 2020, you can say this 5G was launched. It is expected that the 6G will come in some 2030, things like that. So we can see what are the basically security issues in the from 4G to 6G. So in the 4G, basically we can see you are having security issues like this. For example, APT. The APT basically means advanced persistent threat. So basically, it continuously targets some 4G kind of system, 404.5G kind of system. And also, the distributed denial of service could be there, and malicious apps could be there in the 4G systems basically. Now when we move to the 5G basically, so 5G basically use some this, like for example, is enhanced mobile broadband EMMBB. Basically, this is nothing but the enhanced mobile broadband, and URLLCC basically means ultra reliable low latency communication. And also this MMTC, basically this is the massive machine type communication. As you can see, these are the some features, and based on these features, basically like cloud computing is also used in 5G. So basically, based on these features, so we are having the different kind of threats are there also for the 5G communication. 4G different kind of threats, 5G different kind of threat, because the different kind of technologies, different kind of applications are there in the 4G to 5G. So we can see like the software defined radio is also there in the case of this SDN in the 5G. And also you are having this uh, NFV, network function virtualization could be there, things like that in the 5G. Accordingly, so we are having some issues in the 5G. But in the case of 6G, if you go to the 6G, the complexity increase further. So 6G will integrate this artificial intelligence into network control and operations. It rely on extremely high frequency band and support mission critical services like remote surgery, autonomous mobility, and tactile internet. Things like that would be there in the 6G. So these applications require basically very high level of trust, resilience, and security. So as the application grows, definitely the application becomes more and more fine. Then in that case, you require more and more security and trust basically. So therefore, the evolution from 4 to 6G basically reflect a shift from protecting data and devices to protect entire ecosystem, ensuring both privacy and integrity across intelligent, autonomous, and interconnected environment. This evolution demands a more move towards quantum safe security solution. So that is going to be that we are going to see in the next few slides. Okay, any questions up to this point? Okay. Next is the security challenge in the 6G wireless networks basically. So as we progress into 6G, new and more sophisticated security challenges emerge. One major challenge is the massive increase in the network density, because the number of devices are going to be very, very large in that case. Even compared to few years, you can see yourself that few years back, I think only in a house where 4 or 5 persons are there, you are having only 2, 3, 4 mobiles. But now every person is having 2, 3 mobiles. So this is going to be further diced up in the near future when there is the 6G emerge, because the applications are also growing. Even this, every device in your home is going to be connected. It's going to be some IoT devices could be there. So with the billions of IoT devices connected simultaneously, the number of potential attacks points skyrockets. Basically, the number of devices more, and everybody is connected through internet, through some kind of network, then it basically more security would be required in that case. So because each device becomes a possible entry point for the adversary, because the attacker can attack from any of the device. Once it enters through any of the device, it can basically down the complete network as well. So another challenge is the vulnerability of the terahertz communication. Because there's in the 6G, we are going to use this terahertz communication. So terahertz frequency rely on narrow beams, which can theoretically be intercepted with right equipment. That means terahertz enables ultra fast speed. It basically introduces new kind of eavesdropping risk also. So the idea is that whenever you are using a new technology, it also gives you some features, it also gives you some advantage, but it also brings you more risk as well, security threats as well. So another thing is that 6G will also depend heavily on the artificial intelligence, machine learning kind of thing for autonomous operations and resource management. So like the adversarial AI attacks, like data poisoning, model manipulations. So these attacks, which were only confined to AI, now they are going to be part of 6G also, because these attacks could also compromise your 6G network also. So the most significant security threat is the arrival of quantum-enabled adversary. Now that is a topic actually we are more interested in that. So quantum computers can break widely used cryptographic systems like your RSA, ECC. Your RSA basically reversed Shabir Eldman algorithm that work on the public-private key, and ECC is also a little more advanced than that because the number of keys, the size of the key is less in that case. Elliptic curve cryptography, sorry, making current security protocols obsolete. So basically, this leads to some kind of urgent requirement for ultra low latency, quantum resistant. That means the security cannot be broken by the quantum computing techniques. So quantum resistant security mechanism for mission critical applications. So these combined challenges highlight why traditional cryptographic approaches are insufficient for 6G and why we must transit towards quantum safe alternatives. So this is why this is the problem with the 6G communication in that case. So why 6G needs quantum communication? So basically 6G aspires to support ultra level, ultra secure, as I mentioned in the previous slides as well, then ultra low latency communication across a wide range of applications because the applications demand all these requirements basically. So, however, the classical cryptography cannot cope up with the emerging security landscape, especially when the quantum computers enter the picture. And I think in near future, after 5 to 10 years, quantum computing there, and IBM also leading in that. And you can see if you open the IBM website also, you can see people are also started working on this. So as soon as the strong quantum computer becomes commercially accessible, which is very likely in near future as well, widely used classical encryption scheme will no longer be secure because these security can be easily broken by the quantum computers. Additionally, 6G will support vast ecosystems such as massive IoT, autonomous system, holographic communication, and remote operations. So these applications require complete confidence in the secrecy and the authenticity of the communication channel. Because suppose that you are performing some kind of robotic surgery in the remote, then you require trust basically. You require confidence. You must be 100% secure. Then only you can use these applications. So quantum communication and specifically the quantum key distribution offers security grounded in the fundamental laws of physics rather than computational hardness. So even if an adversary had the infinite processing power, which is likely in the quantum computers, the principle of quantum mechanics would ensure that the communication remains secure. So therefore, 6G need quantum communication not simply to enhance the security, but to guarantee. This is the foundational level. It creates a trusted layer, basically some kind of trust there that protects emerging services and basically tries to bridge the gap towards fully quantum secure infrastructure. So that is why we require the 6G requires basically quantum communication. Okay. So how quantum communication enables 6G security? So basically you can see there, for example, we are using this quantum communication plays important role in enabling for the security for the 6G network. So basically we can see this on the first point is bullet is your quantum key distribution. So quantum key distribution, which is in short is also known as QKD, ensure that the encryption keys are shared in a way that inherently resistant to the interception. Sorry. If an eavesdropper try to monitor the quantum channel, the disturbance created by the measurement is immediately detectable. So idea is that because this quantum mechanics works on the photon, so if everybody tries to eavesdrop that, basically it disturbs this. So as unlike your traditional communication, so this in the quantum key distribution, if anybody tries to do that, it will be immediately detected. So this is the idea in the quantum key distribution basically. So quantum communication also supports entanglement-based schemes which allow for the extremely secure authentication and key generation process. These mechanisms offer stronger assurance than any classical method which can provide. So this is entanglement-based communication is also there. Then also we are having this 6GM for the global ubiquitous, that means present everywhere. Quantum communication technologies combined with the satellite-based QKD and quantum repeaters. that basically enables securing long distance key distribution. So repeaters would be there because the signal cannot travel to long distance, so you require repeaters to enhance the coverage, or to for the longer range you require repeaters. So they extend quantum security across continents, and continents, from one, for example, Asia to Europe and other things, supporting the global vision of the 6G connectivity. Uh, Another thing is quantum communication alone cannot scale to every device in massive IoT system ecosystem, because there are billions of devices would be there. So this is where the hybrid framework come into the picture. By combining post-quantum cryptography with the quantum communication techniques, 6G can achieve end-to-end quantum safe protection that is both scalable as well as reliable. So thus quantum communication becomes a counterstone for the 6G long-term security architecture. So this is one thing. Next is future trends in the quantum communication. So basically, quantum repeaters, long distance entanglement, and your quantum memories. So as quantum communication evolves, several transformative trends are emerging. So the first is the basically the development of the quantum repeaters. So the traditional optical networks use classical repeaters, but these cannot be applied directly to quantum signals due to the no cloning theorem, basically. So this quantum repeaters enables long distance quantum communication by preserving entanglement over long spans, which is essential for building continental scale quantum network, that is from one continent to another continent. The second trend is long distance entanglement distribution. So entanglement is basically the foundation of quantum teleportation and quantum secure communication. So extending entanglements over thousands of kilometers is crucial for building the quantum internet. So we are talking about the quantum internet basically. So the third trend involves quantum memories. So basically these allow quantum states to be stored and retrieved on demand. Advanced quantum memory systems with long coherence times are necessary for multi-node quantum networks, synchronizing, for example, this quantum operation across large distances. So we also require quantum memories. So together these trends basically, like for repeaters, long distance entanglement, quantum memories, these trends represent major building blocks for the coming or next generation of quantum communication infrastructure, and that lay the foundation for the future quantum internet. We require repeaters, entanglement, and quantum memories as well. Another is chip scale quantum photonics. So as we move further into the progression of quantum communication technologies, another set of important trends emerges. One of these is basically the development of chip scale photonics. Traditionally, we can say this quantum communication system require large sensitive laboratory setups. With chip scale photonics, this quantum transmitter detectors and logic elements can be integrated into compact semiconductor chips. So this miniaturization means basically minimizing this size is crucial for enabling practical deployment in real-world networks and ultimately supporting integration with the consumer level devices. So the next trend is also the standardization of the quantum networking protocols. So as in the classic protocols are basically the subset of rules basically where the different operators or different manufacturers, so that the whatever the equipment being manufactured, so that they follow certain rules, regulation. So this is basically what is meant by the protocol. So just as a classical communication relies on well-defined standards like TCP/IP, quantum networks will require their own family of protocols. So that means you require new kind of protocols for the quantum to ensure interoperability, reliability, because one system should work on another place as well, reliability and secure exchange of quantum information. So these protocols will define how quantum states are routed, routed, synchronized, and maintained across diverse network architectures. Okay. So finally, all these basically advancement lead us towards the vision of quantum internet. So this future internet will support secure global communication, distributed quantum computing, and new applications that leverage quantum entanglement across nodes. So this quantum internet has the potential to basically change the reshape cybersecurity, communication, and computation by creating networks that could be fundamentally secure and capable of tasks far beyond the classical networks. Sorry. Another is basically this future trends. We still continue with the future trends in quantum communication. So now this quantum cryptography. So quantum cryptography basically QKD, quantum key distribution, and quantum random number generator, QRNG basically. See what it was, this random number generator, as you might have seen in some of the software also, whether it's a MATLAB, but they are not truly as such random number generator. They are basically following some kind of algorithm, so they are not truly random number generator. But in the QRNG, basically we are basically aiming for true random number generator. So the further set of these trends focus on the security applications of like quantum communication, quantum cryptography, particularly quantum key distribution. That is one of the most important thing. So this is practically implemented. So part of this basically quantum communication. Quantum key distribution is the main focus. So quantum key distributions are now being deployed in metropolitan networks, banking institutions, and even government communication system to provide ultra secure key exchange. So in parallel, hybrid frameworks that basically combine post-quantum cryptography (PQC) with QKD. PQC means post-quantum cryptography, and QKD are gaining significant momentum. So pure QKD system, that means, may not scale well to millions of devices. This may not be possible, specifically for say lightweight, some kind of lightweight IoT systems. This may not be possible. So post-quantum cryptography, which is basically software-based, can complement QKD. So we are requiring both basically cryptography, post-quantum cryptography, as well as quantum key distribution. So both basically complement each other. So they can provide some kind of quantum resistant encryption. That means resistant basically means that cannot be broken by the quantum computing. Encryption for devices that cannot implement quantum hardware. So we require both QKD as well as this post-quantum cryptography. Together with this hybrid system, ensure comprehensive and end-to-end quantum safe communication. Another major trend is basically you can see satellite-based quantum networks. So satellite QKD, quantum key distribution, allows countries and continents across the different countries, across the different continents to share encryption keys securely over very long distance. So it basically bypass the fiber optic limitations. So this trend is already visible in initiative launched by say, some countries like, for example, some countries in Europe, United States, as well as in China. These things. So these development basically collectively signifies the early stage of global quantum communication infrastructure. So the researchers, people have started working in this direction also. So now some introduction part is also required for the cryptography. So the few one or two slides are basically based for this uh, cryptography introduction. So to understand why quantum communication post-quantum cryptography are essential, so we start with some basic concept of this cryptography. So basically, cryptography, as we can see, is essentially the science of securing information. It is used to protect the confidentiality, integrity, and authenticity of the data. Without cryptography, secure communication, whether email, banking, cloud storage, or some other national security operation, would simply not be possible in that case. So cryptography works by transforming readable information known as plain text into unreadable ciphertext using, so basically plain text is converted into ciphertext using some kind of encryption algorithm. So even if people is seeing it, cannot read out what is the meaning of that. So to reverse this process, a secret key is required. The strength of this key determines how difficult it is for an attacker to break the encryption. So this is the key, important thing. The strength of the key determines how difficult it is for an attacker to break the encryption. Because if the attacker can find the key, then basically it can decrypt the encrypted message. So the field of cryptography is broadly divided into symmetric key cryptography and public key, or uh, symmetric key cryptography is simple as compared to asymmetric cryptography. Asymmetric In the symmetric system basically relies on the sharing secret keys. So there is only one key which is to be shared secretly. So that means you can decrypt at the receiver side like that. While asymmetric system use paired, basically it use two kind of keys. One is the public key and the private. Public key is basically used for the encryption, and the private key is basically used for the decryption. So this is asymmetric key, public key for the encryption, and private key for the decryption. So basically, this all these things depends on the digital communication. So this is what is basically meant by the traditional cryptography. So a little bit more on that. So symmetric key cryptography. So in the symmetric key cryptography, the same key is used for both encryption and the decryption. As we can see, same key is used for the encryption as well as for the decryption. That means the key distribution should be such that it should be shared very secretly across the different users. So this approach is extremely efficient and forms the basis of the many widely used encryption standards like AES, Advanced Encryption System. Symmetric key encryption is fast, reliable, and ideal for encryption large volume of data. We can use this for the encryption of the large volume of the data. However, it comes with a significant challenge. The problem is with the key distribution, because both parties must have the same secret key, because the same key is used for the encryption as well as for the decryption. So we need to securely transmit it across the network. And this is the problem basically. To transmit this key securely across the network becomes very difficult. If an attacker intercepts the key during the transmission, the entire communication becomes compromised. So the key is fetched by the attacker, then everything is compromised. So in modern networks, the symmetric encryption is often used for data encryption after a secure key exchange mechanism is completed. So basically, it is vital component of today's cryptographic infrastructure, but must be combined with other methods to address the risk involved in key sharing, specifically in the large scale and multi-user system. Because the sharing of the key, sending the key efficiently without being intercepted is the most important challenge in the symmetric key cryptography. Okay. Now another is asymmetric encryption. So in the asymmetric encryption, also known as public key cryptography, this addresses the key distribution problem found in the symmetric systems. Instead of single shared key, basically it uses a pair of keys, a pair of keys which I just mentioned. One is the public key, another is the private key. So the public key is openly shared and used to encrypt the message, because this is only used for the encryption purpose. Public key. Even if the public key is being intercepted by attacker, it is not going to decrypt it, because for the decryption you require basically private key. So the private key remains confidential and used to decrypt those messages. So the best, some examples of the asymmetric key encryption is the RSA algorithm. So this public key systems are ideal for say secure key establishment, digital signatures, and authentication. Sorry. But they eliminate the need to secretly exchange the keys beforehand, making them highly suitable for distributed system and internet scale communication. However, the problem with the asymmetric encryption is computationally it is more expensive. It is require more complex operations and more computationally expensive as compared to the symmetric methods. Furthermore, with this quantum computing, many of the mathematical problems that basically use this asymmetric encryption, such as basically it works on this algebra, so where you require some kind of integer factorization and discrete logarithms and all these things become vulnerable, because the quantum computer can work very well in this direction. It can break all these things basically. So this is one of the main reason why the transition to the quantum safe cryptographic algorithm has become urgent or rather important, or it becomes rather necessity of that. So now we talk about the quantum cryptography. So the quantum cryptography basically it emerges from the intersection of cryptography and the quantum mechanics. So it's a combination of both cryptography as well as quantum mechanics. So the central motivation or the main motivation behind this quantum cryptography is the threat posed by the quantum computers to classical encryption system, which I mentioned also in the previous slide as well. So quantum computers, through some algorithms like Shor's algorithms, basically, they can efficiently break this widely deployed asymmetric cryptography schemes, for example, RSS and elliptic curve cryptography, ECC, and Diffie-Hellman as well. So this means as the quantum computing becomes practical, classical cryptography infrastructure becomes increasingly insecure. So that is the problem. So that's why we are going for this quantum complication kind of thing. So this quantum cryptography approach security in a completely different manner. And instead of relying on mathematical hardness assumption, which is the traditional method of cryptography, it relies on the laws of quantum physics. These laws states that as the act of measuring a quantum states inevitably disturbs it, this principle forms the basis of quantum key distribution, which ensure that if eavesdropper attempts to intercept the key during the transmission, their presence is automatically detected. Because basically it is disturbing some kind of quantum state, basically. So as soon as the eavesdropper tries to intercept something, the quantum states are disturbed and the presence of eavesdropper is detected. So basically, we are also using this quantum mechanics for our advantage. So while this quantum computer threatens many existing cryptographic systems, not all these cryptographic algorithms becomes vulnerable. Some schemes, particularly those based on the lattice problem or the hash-based system, remains resistant in that case. That means the quantum computing is not going to create problem for hash-based systems or other hash-based systems or the lattice problems. So these growing quantum threats basically makes it rather essential to understand why algorithms remain secure and which particular algorithms remain secure and which algorithms do not remain secure in that case. So quantum cryptography therefore plays a crucial role in safeguarding the confidentiality and the authenticity of the future communication system. Now, quantum cryptography is a solution to uh, 6G security basically. So in the near future, this quantum cryptography, specifically this QKD, quantum key distribution, provides one of the most reliable security mechanism available. So QKD basically guarantees that secure sharing of cryptographic keys by leveraging this fundamental principle of quantum mechanics. So unlike your this classical encryption, which can potentially be broken by the future computational advancement, QKD offers unconditional security, even a quantum computer cannot crack it. So in practical deployment, QKD can be used to secure critical communication links such as 6G front haul or the backhaul connections, satellite to say ground communication, and sensitive government or financial networks. So QKD ensures that even sophisticated adversaries cannot compromise the secrecy of the keys. So, however, this quantum communication is not yet a universal solution. It requires some kind of a specialized hardware, has limited transmission distance without quantum repeaters, and may not scale easily to small IoT devices. So, these are some issues with that. So, therefore, integrating QKD into real-world network requires hybrid classical quantum architecture and trusted nodes. So, despite these limitations, QKD remains one of the most powerful tools available today for achieving quantum resilient security and serves as basically some kind of foundational technology you can say for future communication networks in that case. Now we move to the some quantum algorithms and the importance of the Shor and the Grover algorithms basically. So to understand why quantum computer pose such a significant threat to cryptographic system, we must explore some kind of quantum algorithms, particularly Shor's and Grover's algorithms. So quantum algorithms take advantage of quantum phenomena such as superposition and entanglement, enabling them to process information in ways that classical computers cannot. So that's why they are so fast actually. The Shor's algorithm revolutionized the field by showing that integer factorization and discrete algorithms could be solved efficiently on a quantum computer. So these problems form the foundation of basically these things like integer factorization, discrete algorithms. These are basically used in the RSA, DSA, and ECC. So if a large-scale quantum computers becomes practical or operational, in that case, these algorithms can be solved in the polynomial time. That means they can all the security provided by these algorithms could be very easily compromised. So Grover algorithms, on the other hand, provides a quadratic speedup for unstructured search problems. While it does not completely break asymmetric algorithms like AES or hash algorithms, it drastically reduced their effective security level. For example, this AES 128 would effectively provide only 64 bit of security against a quantum adversary. That means it is scaled down to 64 only. Therefore, these algorithms demonstrate how quantum computing fundamentally alters the security landscape. So they highlight the urgent need for cryptographic system that can withstand quantum attacks and motivate the transition to post-quantum cryptography. So another Shor algorithm, this is basically invented by a professor of MIT, Professor Peter Shor, basically. So this Shor algorithm is a quantum algorithm designed to efficiently solve two mathematical problems. One, I think, was integer factorization, breaking large number into prime factors, and second is the computing discrete logarithms. So these two problems are the mathematically foundation of widely used public key cryptography that we use presently, like RSA, Diffie-Hellman, and ECC, elliptic curve cryptography. So Shor algorithm is a quantum polynomial time algorithms that find the prime factors of a composite integer n by reducing the factorization problem to the problem of order finding, so which a quantum computer can solve very efficiently using a technique which is known as the quantum Fourier transform, QFT. So Shor's algorithm uses the ability of quantum computers to process many possibilities at once and then extract the hidden periodic pattern that reveals the prime factors of a large number. So basically, this quantum computer work in particularly well to solve all these factorization problems and discrete logarithms, which is the backbone of this classical security techniques. So this process allows the algorithm to do in minutes what classical computers would take thousands of years to accomplish. So traditional computing system use thousands or hundreds of years to solve all these things, but the quantum computers can solve it within few minutes. So Grover's algorithm is another which is also invented by Love Kumar Grover of Cornell University. So it is a quantum algorithm that provides a quadratic speedup for searching an unsorted database or solving unstructured search problem. So in classical computing, if you need to find a specific item in a suppose that in a list of n items, so you are having a list of n items without any ordering, without any particular order, you need to check each item one by one. So basically, the classical app search, as you know, will take operation n steps because you are searching one by one in that case, basically. So Grover quantum search would solve this operation square root n times steps only, square root n. So this makes the search process dramatically faster, specifically for the large data set. Because if suppose that n is 100, the square root of n is only 10. So Grover algorithm is a quantum cryptography algorithm that finds a marked quantum algorithm that basically finds a marked item in an unsorted set of, say, size n in the operation square root n times. By repeatedly applying a special operator, and this operator is known as the Grover iteration, which amplifies the probability of measuring the correct answer. So this Grover algorithms makes the correct answer stand out more and more clearly with each quantum iteration, so it can be found much faster than the classical search operations. Okay, now non-threads of the quantum algorithms. So as I told you that AES basically stand for this advanced encryption standard and SHA for the secure hash algorithm. DSA basically stand for this digital signature algorithms. So with the capabilities of these quantum algorithms, several real and significant threats emerge. The first major threat is quantum cryptanalysis, targeting say public key systems because sure algorithm can break RSA, ECC, and DSA efficiently, and any encrypted communication or digital signature that relies on these schemes becomes insecure. So this means that even if an adversary cannot break the encryption today, they could record the encrypted data and later on decrypt it later once the quantum computer mature. Basically, this is a kind of scenario where you harvest now, you record it something now and decrypt later. So this is another very uh, important threat basically. Another is increasing key size or modifying existing classical algorithm does not mitigate this problem. Because normally what you do, as per the Shannon's law also, if you recall that increasing the key size brings more randomness so that it is very difficult to crack this key or crack this encryption. Because the underlying this mathematical problems themselves become solvable on quantum mechanics. So quantum mechanics, increasing the key size won't help you in that case. Another issue is symmetric key systems such as hashing function also face risk. So Grover algorithm provides a square root speed up for brute force key search. For hashing, it improves basically collision search attacks. So this effectively weakens the symmetric security parameters, requiring key side and output lengths to be doubled to maintain security in that case. So these threats underline the necessity of moving towards this quantum resistant cryptography system across all digital infrastructure that use some kind of security, from secure networks to say cloud services, authentication systems, and financial platforms. So these are the non-quantum threats on cryptography basically, on real world application at risk. So we can see these quantum threat extends beyond academic cryptographic system and also affects real world application that we rely on daily uses. For example, many foundational technologies, modern communication securities are also becomes vulnerable because of this quantum computing. So like we are having this virtual private networks is there, VPN, which protect communication across insecure network rely basically, this VPN relies basically on RSA or ECC based kind of key exchange. So secure email standards like SMIME and Wave security protocols such as this transmission layer security, SSL basically stand for this your uh, sec- uh, secure socket layer, and now in place of it we are using this TLS, transmission layer security. It also rely heavily on this public key cryptography. So once the quantum computers can run Shor algorithm at a scale, then the security of this system is basically going to be collapsed in that case. So this some systems like federation system, digital signature used for electronic transaction, certificate authorities, cloud authentication mechanism, and software distribution pipelines, everything is going to be on that risk basically for that purpose. Even emerging technologies like your blockchain, despite being modern, that depend on these classical cryptographic primitives and are also vulnerable because they also use some kind of classical cryptography basically. And so these are all vulnerable to the quantum attacks, specifically this private key derivation and the signature generation kind of thing. So that's why it makes it very clear that the quantum threat is not theoretical. It affects the backbone of digital trust, financial integrity, internet security, and basically it also compromises some a country's national infrastructure. So the urgency is basically to adopt quantum safe alternative, which is driven basically to protect some kind of real world application from future quantum adversary. So basically we should be prepared when the quantum computer is installed at a large scale, then we should be ready with the countermeasures also. So non-quantum threats on cryptography. So some basically real world application potentially broken by the quantum computing. So I will quickly go through it. So blockchain basically technology is often viewed as inherent secure due to its decentralized nature and cryptographic foundation. However, it is important to understand that blockchains, whether public or private, are fundamentally depend on the classical cryptographic algorithms. So most blockchains rely on elliptic curve ECC, basically cryptographic, for generating this private public key pairs, creating digital signatures and validating transactions. So like VPN also use RSA, ECC also, VPN also use this basically for key exchange. So this set affects not only the cryptocurrencies but also the government blockchain initiative, smart contracts, the digital identity system, supply chain blockchain structures, things like that. And even systems that attempt to hide public keys are not entirely immune because the moment a user makes a transaction, their public key becomes visible on the chain. So that is also makes this blockchain cryptography also one of the most risky area in future in the quantum era, basically, when the quantum computers would be in vogue actually. It highlights why this quantum safe or post-quantum blockchain framework must be explored proactively. That basically highlights the need for that basically. Okay. So this we can see, this is one example where you can see this private key, public key, Bitcoin address is there, and also you are having this elliptic curve digital signature algorithm. All this is going to be compromised in that case. So this particular thing is one example of that. So if quantum computer has only the blockchain address, it cannot undo the hash for process. However, if it has the public key, it can potentially derive the private key as well. So that particular is also from the MIT paper is also there, so that we can see. Okay. So now we move to the transition to post-quantum cryptography, PQC, post-quantum cryptography. So to counter the this vulnerabilities introduced by the quantum computers, this global cryptographic communities transitioning or moving towards this post-quantum cryptography or PQC. So basically, this PQC refers to a classical cryptographic algorithms, those that run on traditional computers and that are designed to be secure even against quantum attacks. So these algorithms are based on mathematical problems that cannot be efficiently solved by quantum computers, unlike RSA and ECC, which can be solved very quickly. Some of these key families includes lattice-based cryptography, hash-based signatures, and code-based systems and multivariate cryptography. So basically, some of these things we are basically using if someone is from communication background, also in the error correcting codes as well. So this lattice-based cryptography, all these things we are using there also. So what makes PQC particularly important for the 6G rise? Its scalability. Unlike quantum cryptography, PQC does not require specialized hardware. It can be integrated into massive IoT network, which is also the coming thing in the future because now we are going to have a massive IoT networks, Internet of Things network, edge devices, mobile phones, and network infrastructure using the software updates. So this makes PQC compatible with existing communication system while providing long-term quantum security. So PQC ensures that even if adversaries harvest encrypted data today, that means this anyhow saves or get this encrypted data today, they will not be able to decrypt it in the future when the quantum mechanics arrive. This is essential for building secure, future-proof communication environments, particularly in the sensitive domains like national security, healthcare, finance, or you can say in the smart cities. All this would be there. Okay. Now, this post-quantum cryptography and quantum key distribution, why both are needed? One is the QKD, quantum key distribution, another is the post-quantum cryptography. So basically, they are going to complement each other. So this PQC, that is post-quantum cryptography, and quantum key distribution serve complementary roles rather than competing with each other. So PQC basically provides mathematically secure algorithms that run on classical computers. It offers solution for encryption, signature, and key distributions that can be deployed at scale across millions of devices, particularly for the IoT system. On the other hand, this we are having this quantum key distribution, which offers security guaranteed by the laws of physics. It enables secure distribution of the cryptographic keys without any something with no mathematical algorithms can offer also. However, this QKD requires specialized hardware, quantum channels, and often cannot be deployed at the scale of at every day or all the computer devices. So this is why both approaches are essential, PQC as well as QKD. So PQC ensures scalability and broad adoption, while QKD secures high-value communication channels such as backbone links, government communication, very secure channels, data centers, and some kind of secure satellite links also. So by combining PQC and QKD, we can build hybrid architecture that can ensure both end-to-end quantum safe. We are using the word quantum safe in this era of quantum computing. Quantum safe security across both practical and high assurance domains. So this dual approach using QKD as well as PQC provides the strongest and most future-proof protection as we move to the quantum era. Okay, now next we move to the post-quantum asymmetric crypto algorithms. Lattice-based cryptography, basically. Okay, so here one of the most promising and widely adopted families of post-quantum algorithm is lattice-based cryptography. These schemes rely on difficulty of solving certain lattice problems, which are believed to be resistant to both classical as well as to the quantum attacks. So lattice problems involve finding the shortest vector or finding solution to noisy linear equations, task that becomes extremely challenging in high dimension. So several important developments have shaped this particular field. For example, this foundation, Ajit Tal's foundation work in 1996 showed that how worst case lattice problem can be used for cryptography. In 2005, another researcher introduced the learning with errors, LWE, learning with errors problem, which can become the basis for the variety of secure encryption and signature schemes. In 2010, the introduction of ring LWE, that is learning with errors, further optimize these schemes by reducing key sizes and improving the computational efficiency. So lattice-based systems are attractive because they offer a strong security guarantee. They also offer some efficient implementation. Implementation is efficient. So leading NIST standardization algorithms like crystals, Kyber and crystals, dilithium are basically which are based on the lattice problems. So these algorithms provide quantum resistant encryption and digital signatures, making them ideal candidate for securing the future 6G communications. Now, another thing is post-quantum asymmetric crypto algorithms, like code-based, hash-based, and multivariate uh, isogeny-based. So in addition to this lattice cryptography, several other families of post-quantum algorithms contribute to diverse and resilient cryptographic landscape. So code-based cryptography, starting with Macauliffe crypto system, use some kind of error correcting codes, which I mentioned previously also, to secure message transmission. These systems have remained unbroken for decades, offering strong security. But the drawback is that they require also large key size also. So hash-based cryptography provides quantum-resistant digital signature by relying purely on hash functions. So schemes such as strings plus and XMSS offer stateless and stateful variants with strong security assurance, through sometimes at cost of very large signature size. So either the key size is increasing or the signature size is increasing. So yes, this is some of the penalty that you are required to pay for it also as well. Okay, so now also this conclusion is that the basically the key takeaway from this talk is that the future of the communication security must be built upon quantum safe foundations. So basically, we are entering into an era uh, where classical cryptographic system will no longer be sufficient. So the emergence of quantum computing brings both remarkable opportunities also for researchers as well, and significant risk also, specifically regarding the security of the sensitive data and communication channel and national infrastructure. So on the one hand, this quantum communication technologies such as quantum key distribution QKD provides unparalleled security that is grounded in physics, not in mathematics basically. The traditional crypto basically work on the mathematics, but now we are using physics as well. On the other hand, this post-quantum cryptography PQC offers scalable, practical, and widely deployable solutions that can secure billions of devices like in the IoT ecosystem or what is going to be there in the 6G wireless system as well. The 6G also will need billions of devices. So as 6G network integrate with AI, massive connectivity, autonomous system, terahertz communication, and global satellite integration, security must evolve accordingly because we are using so many technologies, AI, massive connectivity, so many things are there in the 6G. So this is the combined adoption of this QKD, PQC, hybrid classical quantum architecture, and ongoing research into quantum networking will be essential, in that case required rather, for building secure system that withstand both current and future threats. So basically in the future we require some kind of international collaboration, some other standardization effects, some things like that, so that we can have some quantum safe techniques, so we can have a communication system which is trustworthy and also secure in the quantum era in the future. So that is the end of the talk, and I thank all the listeners for patiently listening my talk. Anything that we can discuss, we can discuss.
Okay, participants, if you have any question, you can ask.
It is suffering from this throat infection as well.
Yes, sir. Please unmute yourself and you can ask any if you have any question.
So a few questions are there in the chat also.
But-
Okay.
so this presentation, just a minute.
Okay. So there is one question from Shada ma'am. Can we work with quantum principle for improved error detection and correction codes?
Yes, error correcting code would be there definitely. So these are quantum resistant codes, and this could be very well worked there. They also mentioned there.
And second question by Monica Singh. Which kind of algorithm can be used in error detecting in 5G? Okay, as per quantum mechanics technology.
As per quantum mechanics error detection. So
No,
this question is not very clear to me. What is the meaning of
actually,
that?
uh,
Yeah.
basically in 5G, we are not using currently
Yeah.
quantum, what is algorithm?
5G,
Yes,
we are not using these things right now.
yes, yes.
That is basically even the quantum computing, or this is also the experimental setup. And when it is scaled to the large volumes, when it is practically implemented, only in that case you require. But we should start preparing ourselves for this particular thing right now.
Okay. And the last question from Dr. Harpreet Kaur. Please enlighten us about the basic parameter that need to be explored in integrating quantum communication with optical fiber infrastructure apart from compatibility and latency.
I think basically, I think the uh, infrastructure, this quantum communication with the fiber optics,
Yes, sir. Optical fiber.
optical communication and fiber optics. Although the both works on the this photons, but the basic principle is different actually. Yeah, so I think I think the person should basically go through the qubits and all other things. It basically depends on the states. What is the state? Because a particular thing that what is the difference is that the photons, all this in a particular thing can remain in the more than one state at a time. So that is the that's why some particular things like superposition, entanglement, all these things are applicable in that qubit and other things. So these things in traditional fiber optic communication, it may not be there in that case.
Uh, okay, now
Any other
there's last
question?
no, there's a last question. It was the last question. Okay, sir. Okay, okay. Thank you so much, sir, for this knowledge enriching lecture. And sir, if possible, could you please share the slide with us so that we can share?
Sure, sure.
Okay, sir.
Okay, that I will.
Okay, thank you so much, sir.
Thank you very much. Thank you. Okay, so can I
Hello,
leave the meeting now?
Yes, sir.
sir.
Yes.
Hello,
Okay,
sir.
thank you. Hello?
Sir, can you share your PPT, sir?
Definitely. I think Dr. Mukesh
Your
just asked.
presentation is very nice, sir. Thank you very much, sir.
Okay.
Thank you so much, sir. Thank you.
Okay, bye bye. Bye bye.
Okay, sir. Uh,
Okay.
uh,
Should I leave now,
yes, sir.
Mukesh?
Yes, sir.
Yes, sir, you
Yes, sir.
can leave. Yeah.
Okay, thank you.
Okay, participants. Tomorrow we will again start our lecture in the evening from 6 p.m. Thank you so much.
Okay, sir.
Sir.